It's on, right? No, there is no cell phone. There is no cell phone. Yeah. But okay. Yeah.
Good morning, everyone. I should say, as Robin Williams would say, good morning, Natal. The best is always left till the end. And we have three marvelous talks this morning. The first on nematicity, the second on superconductivity, and the third on imaginary time instantons. So the first talk this morning will be given by Indranil Paul. Indranil's from the Laboratoire MPQ and the University Paris Diderot, and he's going to tell us about nematic criticality in correlated metals and the effects of the lattice and impurity. And we're going for 20 minutes plus discussion.
Oh, really?
I don't know.
No, 25, 25.
25 minutes.
Yes,
plus
please.
discussion. Okay, very good. Okay.
Panic. Okay, thanks a lot, Piers, for the introduction. And thanks a lot to all the organizers for asking me to be here. It's both an honor and a great pleasure to be part of this wonderful workshop. So what I'm going to talk about is about nematic criticality, motivated by the physics of the iron-based systems. And so I noticed that nobody really spoke about nematicity in this workshop. So I prepared a sort of one-slide introduction to the topic for the students in the audience, if there are still some remaining. So before that, let me acknowledge my collaborators. So the theory work was done mostly with Marcus Garst, who is in Dresden, and my student Dimitri Labat at Paris Diderot. And we were very much inspired by the Raman response experiments done by Jan Gallet, who is a colleague of mine at Paris Diderot. So what is a nematic phase of matter? So it's a term which is borrowed from the subject of liquid crystals. So in these systems, there are molecules which are rod-like. And so when they are rod-like, you can imagine these rods can have some direction. And at high temperature, these rods, they are randomly oriented. So when such is the situation, then x, y, and the z directions, they are indistinguishable. Okay? So one can think of it as an isotropic phase. Whereas below a certain transition temperature, these rods align and choose a direction, and that breaks the discrete rotation symmetry of the underlying system. Okay? So that's a nematic phase of matter. And it turns out that this property is what's used mostly to make the LCD flat screens. So we owe it to the nematic property of matter for you to spend your money on those large flat screens. So the question here is that, well, this is good, but to understand these things, these properties, it's enough to look at statistical mechanics of classical objects. And so the question that people have been asking for a while is whether electronic correlation-induced nematic phases exist or not. Okay? So it's a question which, to the best of my knowledge, is of the order of 20 years old. and you can go back and look at these nice reviews, which were mostly written before the iron-based systems were discovered. So the field got a big boost in 2008 when the iron-based systems were discovered. And of course, these systems are celebrated for their high temperature superconductivity. But it turns out that they are also some of the best known systems where nematicity in correlated electrons can be studied to their nitty-gritty detail. Okay? So what we are interested in over here is actually this blue line over here coming down. It's a schematic phase diagram as a function of temperature, and think of it as doping. And so it's at this temperature that the four-fold symmetry of the underlying unit cell gets broken. Okay? So when this phase transition occurs, then both the electrons, so here I am showing it as a cartoon, you can imagine a circular Fermi surface then becoming elliptic over here, so that x and y are no longer the same. And at the same time, the underlying lattice, it goes from being tetragonal to orthorhombic. Okay? So they happen at the same time. You get to break the symmetry only once. So what is called a nematic transition is also an orthorhombic transition. And one can immediately ask the question that what is the driver over here? Okay? So it's an egg and chicken problem. And if I come to the last part of my talk, what I'm going to argue is that it's an egg and chicken problem with some very special characteristic where you can actually very sharply and qualitatively distinguish which one is the egg and which one is the chicken. Okay? So to the best of my knowledge, this is the only example where such distinction can be made. So based on that, actually, what we know is that this is indeed an electronic correlation-driven transition, and that's why we like to call it a nematic phase transition. Okay? So that's sort of as a slide of introduction, and now let me move on to the main part of this talk. So what we are interested in, so I have thrown out all the details of this phase diagram, and what we have over here is just this nematic transition which can be tuned to a quantum critical point. And I'm going to pose certain questions related to the properties of matter close to this nematic quantum critical point. Okay? So here is the outline of the talk and the list of questions. So the first question that I'm going to ask is that as we come arbitrarily close to this nematic quantum critical point, is the electronic phase of matter a non-Fermi liquid? We know that there are countless examples in the field of magnetic quantum critical points, whereas you tune the system to that quantum critical point, beautiful non-Fermi liquid physics is observed. Okay? So there are countless examples of that in the field of heavy fermions. And one way to think of it is whether the same happens if it is in the charge sector, if it is a nematic quantum critical point. Okay? The second question that I will address is whether BCS pairing is promoted by fluctuations around the nematic quantum critical point. So if you see a nematic quantum critical point in the phase diagram, is it going to buy you superconductivity or not? Okay? And the third question that I'm going to address is that, so imagine you have some nematic degree of freedom and you can build or calculate its susceptibility. In general, this susceptibility is a function of wave vector and frequency. You can take that wave vector and the frequency to 0 in two different ways. Okay? So one way is like so, which is the static way, and the other one is the dynamical way. And the question is whether these two limits coincide or not. So at this level, it sounds like a very mathematical exercise, but when I will come to it, I'm going to argue that this has very, very important implications in terms of understanding certain experiments. And it is actually this question which is eventually going to determine which one is the egg and which one is the chicken. Okay? So why did I line up this particular set of three questions? And it's really not by accident. So the motivation of that is that all these three questions, if you really want to go to the answer of them, one has to go and look for physics beyond electron-only models. Okay, so that's really the theme of this talk. So for example, in order for the first question, if you restrict yourself to only electron models with interactions, then you will conclude that close to the quantum critical point, this state of matter is indeed a non-Fermi liquid. Okay? Whereas what I will argue is that once you put back electron-phonon interaction, the answer in fact is a no. Okay? For the same physics, you might think that having a nematic quantum critical point is very nice for boosting your transition temperature of the BCS instability, whereas by the time you have taken into account the acoustic phonon interaction, the answer would seem more sobering. Okay? And the third question is actually quite interesting because depending on what ingredient you put, you will come up with various answers. So for example, if you restrict to only interacting electron problems, we will say that these two limits do not commute. Okay? So there is a non-analyticity sitting over there. Whereas when you look at the problem by introducing impurity effects, which give you elastic scattering, then you will conclude that actually these two limits do commute. And then when you realize that, well, it's not the end of the story, I also need to put electron-phonon interaction, then it will turn out that the answer, in fact, is no. Okay? So going from then this yes and no has some important implications, and once again, this is which is going to distinguish the egg from the chicken. Okay? So that's the plan of this talk, and also the main message of this talk. Okay? So let me move to the first part of the first question and try to argue why acoustic phonon interaction preserves a Fermi liquid arbitrarily close to a nematic quantum critical point. Okay? So the point to understand over here is something I have already said before, that a nematic transition is also simultaneously, by definition, a structural transition. And you see that very well where an elastic constant is softening to 0 as you come down in temperature. Okay? So let's keep that idea in mind and take a step back and think of something much simpler, which is from the textbook, which is an elastic medium. And let's imagine this elastic medium has an acoustic instability. Okay? So over the next 2 slides, I'm going to just remind you something which comes from the textbook. So when you have an elastic medium, its free energy is described by the components of the strain tensor. So here, the various U's are the various components of the strain tensor. And of course, there is some stiffness. So these are like springs, and there are spring constants. And the spring constants are the elastic moduli. Okay? So if you have tetragonal symmetry, then there are 6 independent elastic constants. So for example, now, if there would be an acoustic instability which takes a rectangular shape into a square shape into a rectangle, then that happens when this orthorhombic elastic constant goes to 0. Or for example, when a square turns into this rhombus shape continuously at a phase transition, that happens when this one particular elastic constant goes to 0. Okay? Now, these strains, they define not just the uniform part of an elastic medium, but there are also the acoustic phonons, which are finite wave vector excitations of the elastic medium. And so the same free energy actually describes the acoustic phonons. So now you will think in terms of the dynamical matrix. Okay? And when one works out, it's a very well-known result that the acoustic phonon dispersion, it's linear in Q. Okay? And the velocity goes as the square root of the elastic constants. Now, the only thing to keep in mind in order to understand the physics that I am going to emphasize is that when you excite acoustic phonons along generic directions, then you are exciting multiple elastic constants. Okay? It's only when you do excitations around certain high symmetry directions that you excite a single elastic constant. For example, if this is x and y direction, then if the displacements u are along like so, and the wave vector q is like so, or vice versa, only then you will excite the single orthorhombic mode. Otherwise, it's always a mixed mode. Okay, so that's the main message to keep in mind. So if this is the case, then you can immediately realize that if this elastic medium goes through an acoustic instability, then only one elastic constant goes to 0, and the remaining elastic constants are all finite. Okay? So what that means is that if you want to see criticality, which in this language is the vanishing of an acoustic phonon velocity, you will notice it only along those two lines. You deviate out of those lines, you will see a partial softening and then a flattening, which in the language of critical phenomena would then imply that only along those two lines you have a diverging length scale. Anywhere else, because of those finite elastic constants, your correlation length will not be able to diverge, it will be cut off. Okay? So this introduces the concept of momentum anisotropy when you think in terms of critical phenomena. Okay? So this is an inherent property of an elastic medium and acoustic instabilities in an elastic medium. So now you may ask the question, why am I bringing in all of that? So let's bring the electrons back in the problem. And the only point here is to keep in mind is that there is a symmetry allowed linear coupling between the electronic nematic mode and the orthorhombic strain. Okay? And therefore, the electron nematic modes, they inherit these critical elastic properties. This particular aspect that criticality is direction dependent. Okay, so that's sort of the main physics. So let me now move a little bit fast. And okay, so before that, I will connect with Premi's talk. So on Monday, you heard Premi talking about when strain couples to square of order parameter. Okay, so that is the celebrated Larkin peak in physics. And what I am talking about is when strain couples linearly to order parameter. Okay, and this I am going to call it's Larkin was among the first people to discover this effect also. So I'll call it the Larkin-Levenhuk physics. And in the two cases, actually, the results are somewhat opposite. So in this case, you will see that because criticality is only around certain high symmetry directions, it means that critical fluctuations are suppressed. Okay? So how do you see it from the electronic point of view? So here, so one can think in the Ginzburg Landau paradigm. So the free energy associated with a phase transition has a mean field component and a fluctuating component. So that's all I have written over here. Now notice I put a over here and a B over here, and you may think that this is a typo, because in most cases, actually, A is equal to B. What that means is that when you go to the phase transition, second order phase transition where A equal to 0, simultaneously this quantity goes to 0, implying divergence of a length scale. Okay? So it was these people, Larkin, Levenhuk, and their collaborators, who first asked the question, can there be phase transition where B is not equal to A? Okay? So you can ask, how can that happen? When you look at this kind of an expansion and you allow only analytical terms, you realize that the only way that can happen is if B is a function of the various angles of the Brillouin zone rather than its modulus. So let's imagine, so in the next slide I'm going to show this angle dependence coming out explicitly, but imagine for a moment that this is indeed the case, then you see immediately that B will be equal to A only along certain directions. And these are the high symmetry directions typically. Okay? For all other directions, B will be greater than A, and so there is no criticality in the sense of a diverging length scale. So how does this angle dependence come? It's very easy to see this. Here is the coupling between the strain and the electronic nematic variable. And so this gives rise to a correction. Okay? So this correction has, you can see it has a very simple form. And because derivatives enter, the numerator is q square. And you can put this frequency to 0. And we know that the acoustic phonon dispersion is linear. So here, the numerator is q square, and also the denominator is q square. Okay? So what remains behind is not a moduli dependent, but only an angular dependence. Okay? The only point I want to emphasize is that it may seem that this is just a second order perturbation answer, but actually this follows from translation invariance. So the structure of it is protected by that invariance. Okay? So you can look at this problem order by order in the electron phonon coupling, but this particular feature is not going to change. Okay? So when that happens, now you can see that the form of the susceptibility around the critical susceptibility is going to be very different than what we are used to. Okay? So because of this angle dependence. So let's go to the right coordinates which are the critical directions and look for deviations. So if you walk along this q1 direction, which is the critical direction, then the inverse of the susceptibility just goes as q square. Okay, so that's the standard behavior. Now, if you deviate out of it, then you realize that there are these angular dependencies, and so the angles, they come as ratios, and the expansion should start from the square power, because that's the only thing that is consistent with the tetragonal symmetry. Okay? So at the end of the day, the critical susceptibility has this form, which is very, very different from what we are used to in textbooks. So all of that can be shown in a visual manner like so, that if you forget the lattice coupling, you would, and on top of that, the iron-based systems, they're quasi two-dimensional, you will have a critical volume the volume of momentum space, which will contribute to criticality, will be a cylinder and will have an effective dimension 2. Whereas once you put the effect of the finite shear modes, you will see that the critical modes, they are restricted only to these two high symmetry directions, and this effectively leads to a raising of the effective dimension of the phase transition. Okay? So it means that this phase transition becomes Gaussian. And so the critical contributions, they are really subleading, and for all practical purposes, you can forget about that. So effectively what that means, that you have a second order first transition, but you don't have criticality. Okay? And so this leads to such a phase diagram that in the absence of the lattice, the nematic quantum critical point would be here. This would be the finite temperature line. And now, once you add the coupling to the lattice, so first it shifts to a different value, and also it shifts in temperature. And this R naught, one can write it down in some dimensionless parameter as the actual phase transition minus the virtual phase transition temperature divided by Fermi temperature. And then it's a very important parameter that measures the electron phonon coupling strength. Okay, so it's a dimensionless parameter of the theory. So in terms of the dimensionless parameter, then there is a secondary effect, which is as you come down in temperature, there is a temperature scale below which you will see this lattice cutoff coming into play. Okay? And so there will be a non-Fermi liquid to a Fermi liquid crossover, and so arbitrarily close to the quantum critical point, you will say that there is only Fermi liquid. Okay? So that answers the first question. So now, because I'm running out of time, so I'm going to say very quickly about why BCS pairing is not promoted. Well, you can see that it's basically because of this this cutoff effect. Okay, and the point is that if you don't put the electron-phonon interaction, it actually comes as a puzzle. Because when you look at a system close to a nematic phase transition, you will realize that the interaction actually promotes BCS pairing. It is attractive. One can show this. Okay? So based on that, people have thought that, well, if nematic interaction is helpful to BCS pairing, then if I come close to a nematic quantum critical point, this interaction is even boosted, so there should be a TC boost, right? Now, the only system where this can really be tested is actually the doped iron selenium, okay? Where you know that there is a nematic quantum critical point over here, and there is no evidence of TC boost, okay? And what we think is that we understand why this is happening. It's basically this cutoff effect coming into action. So the fact that there is a critical point is immaterial, okay? So let me just move all of that and show you some calculation of my student. So what he's doing is that he's just calculating some BCS eigenvalues as a function of coming close to the nematic quantum critical point. So when the electron-phonon interaction is weak, you indeed see a large response. But the moment when you put the electron-phonon interaction and make it sufficiently strong, you see that there is absolutely no effect of the nematic quantum critical point in the calculation of the BCS eigenvalues. Okay? So now, very quickly, in the remaining few minutes, let me come to the third, in the remaining 30 seconds, at least let me motivate why this is an interesting question, okay? So the point is that this static limit is the object that enters into thermodynamics, and you expect this object to diverge at a second order phase transition. Now, this object, because the nematic order parameter is a component of a tensor, it's very difficult to measure it, okay? One way is to do it by light scattering experiments involving 2 photons. So you have 2 photon polarizations, and so that gives you a rank 2 tensor, okay? But this way, it's a spectroscopic probe. What you are really doing is actually you're measuring some imaginary part, and using Kramer's chronic, you calculate such a susceptibility. But this would be useless if these 2 quantities are not the same, okay? Now, okay, so I really should not go through the arguments, but just give you the answer that when you look at just electron-electron interaction, the problem is that you have lifetime to electrons, okay? When you have just electron-electron interaction. But you are interested in the 0 frequency limit. And that's where also the lifetime is, the inverse lifetime goes to 0. In other words, the nematic the polarization, it can be thought of as related to the conductivity, okay? This is a hand-wavy argument. And what happens is that if you forget about elastic scattering, then you will have an imaginary part which is diverging, and we'll see that this object goes to a constant. And that involves a non-analyticity. But this non-analyticity gets cured the moment you put elastic scattering back in the problem, okay? And then you can show that the static and the dynamic limits actually converge, okay? So this you see very beautifully in the Raman response, the fact that there are critical fluctuations. And you can calculate, you can measure a temperature scale out of it, but then you notice that this temperature scale is different from the thermodynamic instability temperature scale. So what is actually happening is that you are missing the lattice part, okay? So at the end of the day, when you put the lattice back, the static and the dynamical limits are not the same. You can work it out yourself, okay? So, but this also gives a big power, because what it's also telling us is that the Raman response is only measuring the electronic component. It doesn't care that there is an electron-phonon coupling. So if you see criticality or phase transition feature in Raman response, it has to come from the electrons, okay? And this is how you identify the egg from the chicken. Sorry for overshooting. So these are the summary, and thanks a lot for your attention.